Hello everyone, and welcome to this video titled Applied Optimization Problems. In this video, I'm going to be taking you through a preview version of a Knewton Alta homework assignment that is also titled Applied Optimization Problems. So please understand that this is a preview of the assignment. So the questions that I see in this video may not be exactly the same questions that you see when you go to work on it on your own, but the objectives should be the same and the methods used to solve the problems, should be similar. All right, so here we are at Knewton Alta's site, and this is a preview of the Applied Optimization Problems assignment, which for this particular course I'm in is section 4.7. So in the upper right-hand corner, you should see a mastery bar. This tells you how far along you've gotten in the assignment. Next to that, an activity log, which shows you all the objectives in the assignment. So this one has 4 objectives broken up into 2 headings. So optimization problems in a geometric context, and then optimization problems in other contexts. Then back on your main screen, you should see a current objective. Then beneath that, a question related to that current objective. And at the bottom of every question, you should find a feedback option somewhere. So if you notice any issues with the question itself or the answer explanations after the question, you can send feedback directly to Knewton support, and hopefully someone will get back to you relatively quickly with a way to help you fix your issues. You, of course, will not see the instructor cheat option. It's for instructors only to fill in correct answers. I'll try to avoid using this because you won't have it. But you should be able to find a more instruction option. So if you're working on an objective or a problem and you forget the material or need to brush up on it, need some extra help, click on more instruction or open up the more instruction option. And you should be taking this some reading to do or videos to watch or both related to that objective. And hopefully reading through that will help you, get through the assignment. All right, so the first objective I'm looking at is solve optimization problems involving area or volume. All right, so an optimization problem is one in which you're going to be asked to optimize, which means maximize or minimize the value of some quantity. So here it's going to be area or volume. So we're going to be asked to find the dimensions of some object, to minimize or maximize its area or its volume in this particular objective. So I'm going to read through this question. There's a nice diagram to go along with it. I'll even draw this up on paper, and then we'll go about seeing if we can answer it. So here a farmer is constructing 3 equally sized pens against the side of a barn for his animals, as shown in the image below. So this, so you see the barn, again, I'll draw this on paper real quick, but this is the barn down here, and these 3 rectangles are the 3 equally sized pens. So they're already telling us X is the length of the side of the pen perpendicular to the barn, and Y is representing the length of the side parallel to the barn. So this farmer has 152 feet of fence to construct these pens. No fence is needed along the barn. Okay, so this side down here where there's the barn, no fencing is needed for this side here. So the question is, what is the maximum possible area for one of the pens? All right, so one of these three. So we're going to find the maximum possible area for one of the pens. It says you may enter an exact answer or round your answer to the nearest hundredth. All right, that's 2 decimal places. All right, so I'll draw this up. All right, so we got this diagram. So you got this, so they said there's a barn down here, right? So this side is part of the barn, so we don't need fencing for this side. And then we're constructing 3 equally sized pens in a rectangular fashion where one of the sides is on the barn. So I'm gonna make I'll try to make these as equally sized as possible. So again, these 3 should be equal. So again, pen, 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 right? 3 pens. And they said that, the side perpendicular, these side lengths perpendicular to the barn are X feet, right? They said we had 152 feet, so this should be in feet. That's X feet, X feet, for all these sides perpendicular to the barn. And one they mentioned was the side parallel to the barn was Y feet. Okay, so here's the diagram they gave us. Now, the only other piece of information I was given was that this farmer has 152 feet of fencing to work with. So I read through the question, and then you're going to label, certain unknown quantities with letters, just like in any other word problem from like an algebra class. You read through, assign expressions or letters to your unknown quantities, which, they did that for us here. In a future question, I'm sure we're going to have to make up some letters ourselves. And then, you have certain conditions, write down key information. All right, so I'll just put like info over here, right? Key information. And maybe make a diagram, which again, they gave us a diagram here, a picture. We are probably going to have to draw a picture ourselves for, some question after this. We'll see. We'll see how the assignment goes. Now, I'm going to tie this information to the letters that were being used. Make a little equation out of this. So again, I'll just highlight in a different color here in this magenta color, all the pieces of fencing that we're actually using. All right. So there's X feet, X feet, X feet, X feet, and then this, Y feet across. So to make a little equation involving X and Y, and then our information here, see, I had 4 of these X feet pieces, right? So 4X, and then add to that this Y foot piece parallel to the barn, right? That should be 152 feet, right? So you might call this a condition or some sort of restriction on X and Y here, that whatever I make X and Y, they have to satisfy this condition. All right, so what we're asked to do is we're asked to maximize So again, all these optimization problems, you're going to be asked to maximize, or minimize something. So the question was, what is the maximum possible area for one of these pens? So maximize the area of a pen. All right, so this area of a pen, so instead of writing out the words area of a pen all the time, I'm going to label that as well. I'm going to call this A, and this should, since it's area, it's a rectangle, we'd have feet by feet. This will be in square feet. So what we're going to do initially, all right, so I did all this initial information stuff first, right? You label unknowns, make a diagram if need be, point out key information, what's given to you, maybe set up an equation explaining how this key information is related to your letters. So then you identify what is to be maximized or what is to be minimized, and then write an equation for that quantity. So write a formula or an equation for the quantity that is to be optimized. So for the quantity to be optimized, right here it's maximizing area again, optimized. Right. So here, the area of a pen, and just one of these three, there are 3 pens here. I just said for one of them. So remember, these are all equal area pens they mentioned in the problem, right? All 3 of these have the same area. So if I took the area of the entire rectangle, which would be length times width, right? X times Y. That's the area of the entire rectangle. So then one of these pens, this what A represents, will just be 1/3 of this, right? So there's a little formula for the area of one pen, right? Say just this pen here, right? They all 3 of them have the same area. Now, this area formula I just put up. So at the moment, we have the area depending on 2 variables, or they would say that, the area is a function of 2 variables, right? Depends on the value of x and y. Well, here in this, this is for a Calc 1 course, we're only familiar really with working with functions of a single variable. Right, so right now I got a function area. My area is a function of x and y. So what we're going to do after that is use your conditions, your key information, to make a substitution. So then use your conditions, which I only have the one condition, the one piece of information here, to make a substitution into this area formula. All right, substitution. There's an S in there. So what I'm going to do is turn this expression that depends on 2 variables for the area of one pen, through use of our information, our condition earlier, restriction earlier, solve this for one of the variables and substitute into this expression. So that way it'll become a function of a single variable that we're used to. So here's how I would do that for this one. So our condition was, 4 of these x feet, right, 4 x's plus the y feet must be 152. So you solve this condition, you solve your information restriction for one of the variables. Now the easiest variable to solve for in this would be y, right, because the coefficient on y is 1. So what I'm going to do here is I'm going to solve for y in my condition. And that would simply be y equals, 152 minus 4x, or negative 4x plus 152, either way. And then this expression, this, 152 minus 4x, I'm going to substitute that into my area formula. So replace this y here with the quantity, 152 minus 4x, and that's going to turn my function of 2 variables into a function of 1 variable. So now we have area of this single pen is 1/3 times x times, and then y is replaced by, this 152 minus 4x. Yeah, and again, this is what we eventually want to get down to. Now, after making that substitution, my area of a pen is a function of 1 variable, which is what we want, a single variable, which in this case is just, x. So I could call this a of x, right? Since it's a function of x now, I could call the area a of x, but I'm not going to do that because might confuse people thinking this is a times x, even though you should understand this is function notation like f of x or g of x right now. But my area depends on x. Now, if I did it the other way around, say I took my condition here, I could have solved for x and substituted it for x and then made this a function of y. But either way, you're trying to get a function of a single variable. All right, so there, take this back up. Here's the picture again. All right, so now I'm working with this. A equals, 1/3 times x times 152 minus 4x. If you want, you could multiply that out. This is just a nice polynomial. Honestly, because, well, I'll just put the 1/3 x in. Okay, I'll put the 1/3 x in. We can come back and factor this a little more even. Actually, I'll just do that in the next line. Now 152 is, that's 6 and 8. That's not divisible by 3. So I've got, if I put the highest powered term first, like we normally do for polynomials, that'd be negative 4/3, x squared, and then plus, 152 thirds x. So this is a quadratic function, this one, and we're trying to find the maximum value of our quadratic function, given certain restrictions. Now you should be able to figure out the maximum value of a quadratic, without use of calculus. Because if you looked at this another way, I mentioned how, these two terms here, 152 and negative 4x, if I pulled negative 4 out of that, you could also rewrite this as negative 4/3, times x times, and then, x, when I pull the negative 4 out of that term, and then minus, and then 4 goes into this, 38 times, right? Would it be 3 for 12, 1, 32, yeah, 38 times. So you could look at it this way as well. All right, so a bunch of ways we could see our function of a single variable. Now, after you make this substitution, okay, maybe I'll do 3 stars here, step 3 or whatever. Uh, After you make the substitution, get your, the quantity you're trying to optimize is a function of a single variable, it would be nice to know the domain. So, now given the restrictions, right, given the physical limitations, given the restrictions of the problem, right, so think of the actual real world problem here. Because if you think about what X represents, remember X represents, these 4 pieces of fencing that I'm using. So I can't use a negative value. Right, so I'll say X has to be greater than or equal to 0. Now, obviously, X can't be 0, so maybe I'll just restrict it to greater than 0, but because you see how this area function, when X is 0, if I replaced X with 0, you'd get 0 plus 0 or 0 times something. You get no area, right? 0 square feet. And I hope that makes sense, right? If all these X's were nothing, there'd be no pins, there'd be no area whatsoever. Right? And then the high end of this, right? Again, think about the physical limitations of the problem. Remember, there are 4 of these X's in this picture, but I only have 152 feet of fencing. So these can't be more than 38, right? I mean, I divided 152 by 4 earlier. So it can't be higher than 38 either. And you can see in my factored version, think about this, right? If I were to plug in 38 to this function, plug in 38 for x, a of 38, the area when x equals 38, this would also be 0 square feet. Because what you'd have then is, you'd have this barn, and then 38 feet, 38 feet, 38 feet, and 38 feet, and then that's 152. So then there'd be nothing to put up here across. There'd be no more fencing for the top. And so you'd have no area. You'd have no rectangles, no pens. So that's why when I plug in 38, no square feet, no area. And then if you were to make a graph, now that we have this function of a single variable, and my horizontal axis will be this x, right? This depends on x, my input is x. And vertical axis will be the area function. So we saw at 0, when x is 0, area is 0. And when x is, 38, area is 0. And this is a quadratic, where the lead coefficient is negative. So the graph of this thing would be a parabola opening down. So there's got to be a place where there is a maximum area, right? This maximum area that we're asked to find. So the max value of area is up here at the vertex. Now, like I said, with the quadratics, you don't need calculus to find the vertex of the parabola. Or if you know where these x-intercepts are, right, the area is 0 at 0, the area is 0 at 38, use the symmetry of a quadratic, say, hey, this has got to be 19, exactly halfway in between. And then I would plug in, 19. But let's go through and actually using calculus though, right? Using calculus, right? Using your derivatives and critical values. What we're trying to do here is we're trying to find, the absolute maximum, what is the largest area over this domain though. So you see I already plugged in the ends, right? At 0 at 0, at 38 at 0, so definitely not the max over there. Find the absolute, maximum value of A on this interval from 0 to 38. So remember going previous videos, previous assignment, we've done this. and you plug in the ends of this interval, which again, I plugged in 0, plugged in 38, you got 0 at the ends. You're seeing that in the picture. And then you take the derivative, right? So a prime, or dA over dx with respect to my x variable here. That's why I wrote it like this polynomial, because again, this is a simple power rule, term by term, take the derivative. And your derivative, when you go term by term here, would be, negative 8/3 times x plus, 152/3. And then you look for your critical values, right? Which again those are values between the ends, right? So values between the edges, in the interior of the domain, where the derivative is 0 or the derivative is undefined. Now this is a polynomial, so the derivative's never going to be undefined. So I think where is a prime equals 0, and this happens at, x equals 19. If you were to set this equal to 0, you'd subtract 152/3 and then multiply both sides by negative 3/8, and 8 goes into 152, 19 times. Okay, you'd have once with 72 left over, and then that's nine more. 80 and 72, 152. So like I saw in my picture, right? Again, using the symmetry of a parabola, quadratic. This has got to have a maximum area when this value of x is 19. Okay, now what is? So now let's find the value of this area, because that's what they want. What is the area when x equals 19? So I go up here to my area function. Now I can go in this version, or this version, or this version. I'm going to go in this last one here, because I pulled out the -4. So this would be -4/3 times, and then again, x is 19, times, and then 19 minus 38. And 19 minus 38 is -19. So that'll turn this into a positive, right? Negative times negative, so positive. And now 19 squared, 19 squared, 361. So we have -4/3. Well, it'd be positive. Positive, 4/3 times 361. And, numerator 4 times 361 would be 1200 plus 244. So 1,444 in the numerator, and then just, 3 times 1, 3 in the denominator, square feet. All right. So that's this highest area up here, right? 1,444, divided by 3 square feet. That is the largest area that just, one of these pens could possibly be if I only had the 152 feet of fencing to make this. Now they did say you could round it to 2 decimal places also, but I'm gonna put this in because they said we could put exact as well. Now another thing, let's go check this in Desmos. I got that online graphing calculator put up. Might as well. So my area function, I called it a of x equals. I'll just put it in with the polynomial version all multiplied out. So there's -4/3 x squared plus, and then 152/3 times x. And again, we said we had to restrict the domain from 0 to 38. All right, so 0 less than or equal to x, less than or equal to 38, based on the restrictions of the actual problem. And look at this. All right, so I'll zoom this out. So you can see parabola opening down, right? There's clearly some maximum value up here of 481.33333. So if I was rounding to 2 decimal places, right, I'll put 481.33, rounded to the nearest hundredth. But if you look at what we put on the paper, 1444 divided by 3, that's the same value. That is this highest value here. And as I said, on the left end, you got 0, 0, right end, you got 38, 0. But the maximum area is this 481.333. .33 square feet or 144 thirds square feet. All right, so back here what I'm entering, and they already got the square feet units in, so I'm just putting that maximum area, and I'll just put, I said I could put exact or rounded. I'll just put the exact 1,444 divided by 3, or that 481.33 if you're rounding square feet. All right, then once you've submitted an answer, it's going to tell you if you're right or wrong, and then you'll have some sort of answer explanation. I would highly recommend reading through these, whether you're right or wrong. If you're correct, maybe you did it in some very inefficient way, and when you read through the answer explanations, you might see that they're doing it in a much nicer way, much more efficient, that you might want to try to do for future problems like that. Definitely read through these if you are wrong. All right, try to figure out where you went wrong, and hopefully you can learn from your mistakes for future questions that are similar. Okay, so moving on. All right, so now that was a optimization problem involving an area or a volume, right? The area of some pen. Here we're going to be asked to minimize the surface area, right? So surface area is the amount of area taken up, on the surface of some three-dimensional object, right? Just on the surface, on the outside. It's kind of akin to the perimeter of a two-dimensional figure, right? Just the outer stuff. So here you have been asked to design a rectangular box with a square base and an open top. The volume of the box must be 16 cubic centimeters. You are asked to determine the dimensions of the box that will minimize the surface area. Make it as small as possible. Where x is the length of each side of the base, and y is the height of the box. In this one, they want us to enter an exact answer. All right, so here they gave us some letters, but they didn't draw a diagram, right? I'll draw a little diagram to go with this. So we're creating this box with, it doesn't say cardboard or anything, but just has to design a rectangular box with a square base. All right, so let's say this is the base. So again, this is a square base and a rectangular box, meaning, all the faces are rectangles. Right? So again, something like this. Okay, so you're creating this box. It said it has an open top, right? So that means there's not a face. There's no material on the top of the box. But the other 5 sides, the front, the back, the right, the left, and the bottom, right, the other 5 sides do have material. And then they told us some things, right? Some information. That the side lengths of the base, they wanted us to call those x, and the volume was given in cubic centimeters, so this will be x centimeters. And it's a square base, so that means it's same length on both sides of the base here, x centimeters by x centimeters. And then they told us also to call the height of the box y centimeters. And then the information given, or the restrictions, the conditions on the box here, is that the volume of this box, which I'll label with just V, the volume of the box has to be 16 cubic centimeters. Now, just like the last problem, I'm going to take the information I was given and relate it to these letters, right? The length and width and height of the box. Well, remember, the volume of a box is how much is inside the box, how many cubic centimeters fit inside the box. And that would be for a rectangular box here, just length times width times height. So that's x times x, or x squared, times y must be 16, right? So there's a nice little equation relating the information I was given, to the dimensions of this box here that they gave us. So we're asked to minimize the surface area So again, I'm going to call the surface area S for, for surface, big S. So remember, like last time, I'm going to write an equation that tells me the surface area, right? Now that's the area of all the faces except for the top, right? Again, it's an open top. So only the front, back, right, left, and bottom, right? The five faces with actual material. So I'm going to write an equation, a little formula here that tells me how to calculate the surface area when the dimensions are, the letters I have here, x, x, and y. Now the bottom has an area of x squared, right? That's just a square. And this will be in, square centimeters, right? This is an area, right? So these will all be square units added up. So that's the area of the bottom plus, and then the four faces around, so front, right, back, side, those are all x by y rectangles. So there are four of those. So 4 times x times y, 4 times xy. So that's the area of the base plus, and then the four faces around the box. And once again, if they had the material on top, I would put 2x squared, but there's no material on top. So no, just the base, just the 1x squared. All right, so and like the first problem, now that I've written a formula for my surface area, it is a function of two variables. Right, there's x's and y's in this. So I'm going to use this information we had from earlier, right? They told us the volume had to be 16. I'm going to solve this for one of the variables and substitute and, turn this into a function of a single variable. Now, once again, in my equation here, with the information given about the volume, x squared times y equals 16. The easiest one to solve for is y, right? If you had to solve for x, there'd be square roots involved because it's x squared, but y is to the first power. So I can solve for y more easily. So y here is, 16 divided by x squared. And then I'm taking this expression, right, this 16 divided by x squared, substituting it for y in my surface area formula. So now we have the surface area, in which we could also call surface area of x, right, using function notation, because when I replace y here, it's going to be all in terms of x now. It's going to be x squared plus, and then this is 4 times x times, and then y becomes, 16 over x squared, which we can simplify a bit. This is x squared, and then 4 times 16 is, 64, and one of these x's cancels. So plus 64 over x, or if you don't like that, you like to rewrite with negative powers. This is x squared plus, 64 times x to the negative 1. All right, so all these are the same. All these are the same. All right, so now that I've written my function of one variable here, right, this tells me how to calculate the surface area of this box when I just know the side lengths on the bottom here, these x values. Now the domain. So once again, x, what is x? This x in here, what does it represent? It represents lengths of sides on a square. So it's got to be positive. Now notice in my function here, it can't be 0, not like the last problem. Right, the last problem had a polynomial. You could plug in anything. So I had equals 0 there was possible. But here, notice I have a denominator of x, so I can't plug in x. So this value of x has to be strictly positive. And then I could, if I want a volume of 16, I could make this square as big as I want to, and then I would just have to shift the height. Right? The bigger you make x, you see how y is 16 over x squared. The larger you make x, the smaller y needs to be so that you still have a volume of 16. So this is it. This is the domain here. I guess you could say just, if you're doing interval notation, 0 to infinity, where 0 is not included. So when we, check the ends, technically we got to do some limits. Because the endpoints are not included. So when we, again, check the ends, take the limit as x approaches 0 from the right, and then the limit at infinity to see if there's a value that the function seems to be approaching on the ends. All right, so we'll do this, right? Now that I have my function of one variable, I know the domain I'm working on. Let us now go through our procedure to find the absolute minimum, right? We're asked to minimize this surface area, this S value. So I go and let's find the absolute minimum of S. Right, now we're going to find the dimensions that make this happen, right? They want just the dimensions of the box. So again, check the ends. Now the ends here, you got to do limits because they're not included. So I would take the limit as x approaches 0 from the right, because again, to go towards 0 here, the left end, I had to approach 0 from the right of this function. Now, if you look at this, look at the way this looks here. This first term would approach 0. 0 is getting something really small squared. But then this next term, 64 over x, would get very, very large. You'd have 64 divided by some really small number. So that'd be 64 times some large number. So 0 plus infinity, that's an infinite limit. All right, so what you're going to see happening, and we'll look at this in Desmos too, but what you're going to see happening is, I input x, and then the output will be this surface area. What we're going to see happening is that as you approach 0 from the right, this value of the surface area is going to go up forever. So definitely not going to have, you're not going to find the absolute minimum with that limit. And then the other way is the same. On the right end of this, the right end of this is infinity. So I'm taking the limit at infinity, limit as x approaches infinity of my surface area function. So again, this first term would be getting gigantic, right? This x squared term would be blowing up, and then 64 over something big would be really tiny. So the first term's going to infinity now, and the second term's going to 0. So this is infinity plus 0 or infinity, right? Very large again. So again, when you're going to look at a graph later, as I go to the far right, as I make x bigger and bigger, also going to go up forever. Right? So it's going up forever to the right of 0 and going up forever as you go to the far right, as you take the limit at infinity. So definitely not seeing the absolute minimum from these, right? These are positive infinity on the ends. So it's got to happen somewhere, for some positive value, between 0 and infinity, It's got to have a minimum somewhere at some critical value. All right, so now we talk about the critical values. So now this is where S prime comes in. So again, I'll just put it this way. You have 2x and then minus, 64 times x to the negative 2. And you could factor this, pull out, they both have a common factor of 2. And then the lowest power of x is x to the negative second. So if I were to pull that out, then you'd have x cubed minus 32 left over, right? And you can double check, that'd be 2, yeah, that'd be 2x, and then minus 64 x to the negative second. So this is undefined at 0, but that's not even part of the domain, right? The derivative here does not exist at x equals 0, but I'm not worried about that one. I'm not going to, because this isn't even part of the domain. I'm going to cross that out, ignore it. Not even part of the domain. And then from this other factor, you can see that the derivative s prime here is equal to 0. That would happen when x equals the cube root of 32, which is not a nice whole number. So there's the dimension of the square base, right? So and then at the cube root of 32, there's got to be a minimum, right? Because again, at the ends it's going up forever. So there got to be a minimum here. Now you could plug in values around this to see that s prime is negative to the left and positive to the right to see that there's the bottom of a valley at the cube root of 32. And if you wanted the value of this surface area, so here's the value of the surface area at the cube root of 32, right? I'm going to plug this into my surface area thing. So that would be the cube root of 32 squared. So I'm going to write that as 32 to the 2/3 power. Remember, this is the same thing as 32 to the 1/3 if you want, cube root of 32. And when I square that, that'll be 32 to the 2/3. And then plus, 64 over the cube root of 32. This is definitely not infinity, right? This is some positive value. So this has got to be the minimum surface area that's possible when the volume of the box has to be 16 cubic centimeters. So there's your minimum surface area. Now that, again, that's not the answer, but I'll punch this in Desmos, you'll see. What they want is the dimensions of the box, right? So remember this x, so this is the cube root of 32 centimeters down here by the cube root of 32 centimeters. And then remember how to find y, right? Y would then be 16 divided by the cube root of 32 squared. All right, so 16 divided by 32 to the 2/3 power, right? That's the cube root of 32 squared. That would have to be the dimension of y to give me this minimal surface area box. So again, I'm just gonna type that in. They said put an exact answer, as long as I'm putting something that is equal. So let me show you. All right, let's go to Desmos, and I'm going to enter my surface area function here after making the substitution, this x squared plus 64 over x function, and we'll take a look at it. So I called it capital S of x, or you can call it whatever you want. Now we had x squared, that was the area of the base, and then those 4 times the area of the sides around after making the substitution was 64 over x. And making the restriction that x needs to be greater than 0, period, right? That was the only restriction. Right, so if you look at this, there, look at that. All right, so you see how to the left, as you approach 0 from the right, going up forever, and then as you go to the right forever, approach infinity, also getting larger and larger surface areas. So you see the minimum down there? That happens when x is 3.1748. Well, look, here's the cube root of 32, 32 to the 1/3 power. 3.1748, blah, 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 right? This is the cube root of 32 for the x coordinate. And this, again, this y coordinate is that minimal surface area I wrote down, which is, x squared. I'll just put s of 32 to the 3rd. And you see that this was that 32 to the 2/3 plus 64 over the cube root of 32 that I wrote earlier. But we're not asked for that. Okay, we're not asked for that. We're just asked for what's the x, what's the y, what are the dimensions of the box that would give us this minimal surface area. Okay, so again, the value of x, I'll just put 32 to the 1/3 power, right? The cube root of 32. And then y had to be 16 divided by x squared. So 16 divided by 32 to the 2/3 power centimeters. Okay. So again, you have to enter an exact answer. So don't punch these in. Don't round. Now, if they said you could round, I would just go to Desmos. Honestly, I know you should be able to do it by hand, but after doing a few by hand, I would go to Desmos and make it quick, and you can highlight a graph and see what the minimums and maximums are. Okay. All right, so here's another minimize surface area problem. So you have been asked to design a can with a volume. So another one where they give you the volume of some three-dimensional object, and you're trying to give me the smallest surface area. So you've been asked to design a can with a volume of 756 cubic centimeters that is shaped like a right circular cylinder, right? So like a typical straight up can, circular can. The can will have a closed top. So this time, instead of an open top, there is actually material at the top. So we have to take that into account when we calculate surface area. So what radius and height, so radius r and height h in centimeters, would minimize the amount of material needed to construct this can? So this is one where I could just, once I set my function up, use Desmos to help me out, or enter, because they're asked me to round my answer to 2 decimal places, or enter an exact answer. So I'll try to find the exact answer first. Let's go through that. So pretty similar to the last problem with the minimizing the surface area of a box, right? But this time we have a circular can. So something like this. I'm making a circular cylinder. Right, that's a nice cylinder. With a radius, right? So from the center to the edge of r centimeters, and a height from top face to bottom face of h centimeters. And we're told that the volume of this can, so again, I'm going to use volume V, has to be 756, cubic centimeters. All right, so using the letters I have here, we can write a little equation for this condition, an equation for this information, like in the previous couple problems. Now, the volume of a solid, right, a prism, like this, and like the box in the last question, the volume of a prism or a cylinder is the area of the base, so pi times the radius squared, that would be the area of the base, the base is a circle, times the height. Area of the base times the height. That should be equal to 756. And once again, we're asked to minimize the surface area. All right, so the amount of square centimeters of material used on the outside of the can. And they did say it has a closed top, right? So that means there's actually some can on top here as well. It's not open. All right, so like before, I'm going to call surface area, big S, and write an equation so that we involve R and H here. Now there's a bottom and there's a top. So the circle on the bottom and the circle on the top. So remember, one circle has an area of pi r squared, but then there are two of those. Right? There's 2 pi r squared. That'd be the area of the bottom plus the area of the top. And then add to that what's referred to as the lateral surface area. So remember, if you were to slice a can down one side and then unroll it, you get a sheet where you got the height. It's just a rectangle where this is the height, and then the other length is just the circumference of the circle, and the circumference of a circle is 2 pi r. So this lateral surface area, the area around the middle of the can here, is 2 pi r times h. All right, so there's the surface area of my can. Now notice it's a function of 2 variables. It depends on 2 letters right now, r and h. So instead of that, I'd rather, again, we want it to be a function of 1 variable. That's where the condition comes in, the information we have. Now this is another one where it would be easier to solve for h. So see, h would be 756 divided by, pi r squared. And then I take this expression with r, substitute it for h, and now we'll have an expression that depends solely on r. So I'm going to call this s of r. It's a function of r is, 2 times pi r squared plus, and then 2 pi r times, and then this h is being replaced by 756 divided by, pi r squared. All right, so some things cancel here. We can simplify this a little bit. So this would be 2 pi r squared plus, and then here, pi's would cancel and one of the r's would cancel. And then 2 times 756 be 1512, 1512. Over, and then just one of these r's, which, like in the last one with the over r, I can write this as 2 pi r squared plus 1512, times r to the -1, if you want to write it that way. But there's our surface area function of a single variable, this radius variable. And now the domain, very much like the last one, the radius just needs to be positive. Again, can't be 0, because I have divided by r here. And it can be, I can make the top and bottom of this thing as big as I want. And now all that would do is just shrink the height a lot. So the bigger, from this relationship right here, if I make the radius huge, I got to make the height really, really small to make sure that the volume is still, 756 cubic centimeters. So the only restriction here is, 0 to, where our values of r just need to be positive. All right, so on the interval from 0 to infinity, but, not including 0. So just like last one, now I'm going to try to find the absolute, minimum value of this s function, this surface area. Now they want the dimensions again, right? They don't actually want the volume. They want the r and the h that would make it smallest. But still, I'll go through the procedure that we would normally go through to find the absolute minimum value of s, of this surface area. All right, so on the ends, once again, there's a huge problem. We're going to be approaching infinity, right? If I'd be taken for the left end here, approach 0 from the right. The limit is r approaches 0 from the right of this. And just like the last problem, this is infinite. Because again, this first term would go to 0, but then this term with the divided by r would get gigantic. So go to 0 plus infinity, right? So we have an infinite limit to the as we approach 0 from the left, or sorry, from the right. And we'll see that in a graph later. I'll make a graph. And then on the right end here, I'm having the limit at infinity, right? The limit as r approaches infinity of this function. And once again, first term would be getting huge. The second term would be getting small. So like infinity plus 0. So another infinite limit. So going up forever to the right of 0, going up forever as you move to the far right, go to infinity. So I'm not getting any minimum value out of these. So it's got to be at some critical value. All right, so now the criticals, and we look at the derivative. So this will be s prime, with respect to r here. Treat r like x, like you would normally x. So I'm just doing a simple power rule. I'm going to look at my s function this way, and then just do a simple power rule for each. So that'd be 4 pi r, and then minus, 1,512 times r to the negative 2. And we could do a little factoring here. Both of these have a factor of 4, and the lowest power of r is r to the negative 2. So if I were to factor that out, you'd have pi times r cubed for the first term, then minus, let's see, 756, and then 328. 4 times 328 would be 1512. Yeah, 1280 plus 32. All right, not 1280, 1480 plus 32. All right, so once again, the derivative is not defined. This s prime is, non-existent when r equals 0, but 0 isn't even in the domain, right? We're only looking for positive values of r. So once again, I'm going to ignore that part. And then this factor will tell me where I can make the derivative 0. Right? S prime is going to be 0 when r equals, the cube root of 328 over pi. Which, it's not a nice number. Now, they do say you can round to 2 decimal places and whatnot, but that's where there's got to be a minimum. So this value of r is going to give me a minimum. And then when I plug, so again, I'm just going to enter it this way. They said you can put it exact. And when this happens, the height, remember, has to be 756 divided by pi times, this thing squared. So I'm just going to write this as 328 over pi. That's to the 1/3 power. So when I square it, that'll be to the 2/3 power. So r would have to be this many centimeters, and h would have to be this many centimeters, to minimize the surface area. Now let me doubly verify that. So again, I'm going to go to Desmos here, enter this function. So again, I think I can enter it with, no, I shouldn't do r because they'll probably confuse it with polar. So I'm just going to call, instead of r, I'm going to call it x again. So this was 2 pi, x squared instead of r squared, right? Again, I'm just calling rx plus 1,512 divided by x. And setting up the restriction that, x or the radius has to be positive, right? All right, so we do that. There's something up here, right? So look, you see, there's definitely a lowest surface area, right? To the left, as you approach 0 from the right, going up forever. And then as you go to the far right, approach infinity, it goes up forever. There's definitely a minimum. And this minimum surface area is, going to be 459.4 something, square centimeters. But it happens at r equals 4.936. Now you could put in 4.94. Right? They said you could round to 2 decimal places. But I'm just going to enter the exact value we found. And that was this, right? I said that that minimum is going to occur at 328 over pi, the cube root of that, so raised to the 1/3 power. See this 4.70877? Oop. Okay, so that's nice that all right. So 1512 over X. Sorry, so where did I go wrong here? Let's see if I divided correctly. 1512 divided by 4. Oh, 378. That's why. So this should be 378. That's better, right? 4.9368. 4.9368. Okay. So again, my apologies. This should be not 328, but 378. When I pulled out that 4r to the -2. My bad. All right, so again, this will be 328 over pi cube root. And this will be, sorry, 378 over pi cube root for the value of r. That'll give you the minimum surface area. And then down here, this will be 378 over pi to the 2/3. Yeah, so I'm glad I went to Desmos and checked that. Right? Always check your work. Always check your work. All right, so I'm going to pop these in with the 378. Those are where the surface area will be minimized. So back on the homework assignment, right? The radius of this can, the radius of the circle at the base, it would give it the smallest surface area, would be 378 divided by pi. And then the cube root of that, right? So to the 1/3 power. And then the height would be 756 divided by, and then pi times, and then radius squared 378 over pi to the 2/3 power. And I'm hoping this is good as an exact and they don't need me to simplify this. Great. Now they probably have it rounded. No, they don't. They wrote it out exact with all the cube root symbols and whatnot. But yeah, so then they might have it round. They might have it rounded in the answer explanations. Yeah, they have it rounded in the answer explanations. So again, 4.94. Right, that's what we saw in the Desmos graph. And then if you were to pop that in, round for the height, height was 756 over pi r squared, rounds to 9.87. But you can just enter the exact value. Okay. All right, so back to another one with area or volume. So this is an open top box. So again, no material on the top. Is to be made from a 24-inch by 30-inch piece of plastic by removing a square from each corner of the plastic and folding up the flaps on each side. What should the length of the side X of the square cutout of each corner, cut out of each corner to get a box with maximum volume? And once again, you can enter an exact answer for X or a rounded to the nearest hundredth value. All right, so again, no diagram this time. So here's what's going on here. So you got this piece of plastic and they gave us dimensions. It's a rectangle. They said it was 24 inches by 30 inches. And they're going to make a box out of this by cutting squares out of the corners. Now all these squares will be the same size. So I cut these out. Again, then we've, crease here, make this square in the middle, and then that'll fold up. So again, I'm removing the corner, removing this corner, removing this corner, removing this corner, and then folding the flaps up, and we get a little box like this. We get a 3D box. All right, so we're making a box like this. Now, they told us these squares that are being cut out of the corners here. So this square, all these 4 squares being cut out of the corners. They told us to call the dimensions of the square x inches. So cutting x inches by x inches. And this is x by x, x by x, x by x. You're cutting an x by x square out of each corner and then folding up the flaps. Well, if I do this, then the height of the box, right, this will be the width of these flaps, which will be x inches. And then this space here in the middle, this square in the middle, or sorry, rectangle in the middle, and it looks like a square, but it won't be. This rectangle in the middle, this is going to be the base of the box, at the bottom of the box. Now the lengths of this base, the length and width of this base here, see this side here? I had a 30 inches across, and then I cut x from both sides. So that new length is going to be 30 minus x, or sorry, minus 2x, because I cut x from both sides, so that's 2x. And same thing with this, I have 24 inches across the whole way. I cut x inches off of both sides, so the new length will be 24 minus 2x. So on my box here, one side is 30 minus 2x inches. The other side is, 24 minus 2x inches. So now we can do the volume, right? We're asked to maximize the volume, right? They want us to find the value of x. Find the value of this x. How big should these squares in the corners be cut off so that we get maximum volume? All right, so again, I'm going to call volume V. Now this is already going to be a function of x, so you can say V of x equals length times width times height. Now I'll put the height first. So we got x times 30 minus 2x times 24 minus 2x. This would represent, and this would be in, of course, cubic inches, right? They give us inches, so cubic inches, inches cubed. So there represents the volume of this box I'm creating. Now I could multiply this out if I wanted. And what I'm going to do here is, I notice that this factor and this factor both have common factors of 2. So I'm going to pull 2 out from both of those, pull a 2 out from this, 2 out from this. So that'll make 4 out here. So I got 4 times x. And actually, I'll pull a negative 2 out from both of those just so we have a positive x. And then you got x minus 15 if I pull negative 2 out of that one. And then x minus 12, if I pull a negative 2 out of that one. So there's a nice also factored form of our polynomial. And then if you want to multiply it out further, 4x times, and then these two, x minus 15 times x minus 12 would be x squared minus 27x plus 180. Yeah. And then putting the 4x in, you got 4x cubed minus, and then 80 and 28, 108, right, minus 108 x, and then 4 times 18, 40 and 32, 72, so that'd be plus 720, that's x squared, plus 720x. Right, this would be x squared in the middle here. All right, so all these are the same. All right, these are all the volume function. Now the domain we'll be looking on, again, think about the problem. I can only plug in non-negative, and now this time I could plug in 0, even though it would make no sense, because then I'd have a box with a height of 0. And you can see that the volume when x is 0, so this will be the value at one end, is 0 cubic centimeters, right? There'd be no box to speak of. There'd be a box with 0 height. Now the other end of this, if you think about the piece of plastic that we started with, one side's 24, the other side's 30. I'm cutting x from both sides, so the furthest I could go is 12, right? If I go more than 12, I'm cutting I'd be cutting more than the 24 inches off of that side. So the max this could possibly be is 12. And you see that the volume at 12 is also 0, right? Because again, if I were to cut 12 and 12, you'd get this fold here, and then you'd fold it up and there'd still be no box, right? You just have a folded up piece of plastic. And look at my function, right? If I plug in 12, one of the factors is 0, you get a whole product of 0. So at the end of my domain here, right, from 0 to 12, the volume is 0. So definitely not going to be the maximum possible volume box I could make. So we got to go about finding criticals, right, critical points. So that's why I multiplied it out here to make, v prime. Go term by term here, that'd be 12x squared minus 216 x to the first plus 720. And then each of these is a multiple of 6. So I'm going to factor out a 6. And then we have x squared, 2x squared, right? 6 times 2x squared would be 12x, minus 6 times 36 is 216. And then plus, and then 6 times 120 36. Wait a minute. Yeah, 6 times 2 is 12. 180, 36, 216. So actually, these are all multiples of 12. So I'm going to pull out another 2 just to shrink the numbers. So that's 12 pulled out. And then if I pull out another 2 out of these, that's x squared minus 18x. And pull a 2 out of that plus 60. Yeah, there we go. Okay. And then I'll just look at this quadratic, see when's that 0. So set x squared. So again, we're looking for critical values. It's not going to be undefined. When is x squared minus 18x, plus 60 equal to 0? I'm going to complete the square here. So subtract 60. Half of this is -9. Squared is 81. So yeah, this is x minus 9 squared equals, 21. And so x could be 9 plus the square root of 21, inches, or 9 minus the square root of 21. Now, the only one that actually makes any sense that belongs to the domain here is the one with the minus, because the square root of 21 is bigger than 3. So this would be bigger than 12. We're only looking for values of x between, x can only be from 0 to 12. So this makes no sense. So the only value that makes any sense at all that actually works would be 9 minus the square root of 21. And that's an exact answer. Now, they did say you could round, right? And if I were to plug this in, we'd get the maximum volume. They don't want the maximum volume, right? They just want the value of x that I would have to cut out for those squares in the corners to get the box of largest volume. So again, just to doubly verify, right? Because again, I made a little arithmetic error with that one problem that I happened to catch with Desmos here. So here was my volume function. So again, v of x equals, I'll just write it out in that factored form. The height was x, then you had 30 minus 2x for the one side, 24 minus 2x for the other, and then we need to restrict this 0 less than or equal to x less than or equal to 12. And look at this picture. So you see, 0 at 0, at 12 at 0, and you see beyond 12, you'd be negative until 15, right? If I were to get rid of the restriction, it would go negative, but then come back and be 0 at 15 as well. But you see, it's positive volumes in between, right? And the largest volume occurs, it's way up here. Let's see, where is this maximum? It's quite large, right? But way up here, there's a maximum somewhere in between 0 and 12. And it occurs here at this 4.417 value. Well, I said that was at, 9 minus the square root of 21. See, 4.4174. So that's what they want. Now you could put the two decimal places, go 4.42, which, I like, since I found the exact, I'm going to put the exact. X equals 9 minus the square root of 21 inches would be the exact value X needs to be to get a minimum, or sorry, a maximum volume. Great. We got a little diagram there. All right, cool. All right, so now we're working with minimizing distance or travel time. So now look, they have a nice little diagram for us in this one. Little, pretty big. So I'll try to recopy that. So here, a farmer's house sits 5 miles due south of a river. The diagram below shows the path that the farmer takes from his house to the river every day in order to bring water to a farm located 6 miles from the river and 3 miles east of the farmer's house. So by choosing a different point P on the river to draw water, the farmer is able to walk different distances to do this task. Find the minimum distance possible that the farmer has to walk. And it says enter an exact answer or round to the nearest hundredth of a mile. All right. So here's this picture, right? They said here's this river. They said the farmer's house is, 5 miles due south. So this is 5 miles straight to the river. And there's a farm that is 3 miles east of the farmer's house, but that is also 6 miles, so it's, further away from the river. It's 6 miles from the river. So here's the picture they're giving us in this farm. And what happens is the farmer walks to the river, straight to the river, to some point P, and then walks to the farm. Draws some water, then walks to the farm. And we're asked to, minimize the distance. So find the minimum distance possible. So the total of, so again, I'll just call this point H for house and this point F for farm. So we're trying to minimize the distance from H to P plus P to F, right? That segment there plus that segment there. Now, this is another one where you don't really need calculus to do something like this. You can use reflection properties. So I'll show you what I mean by that. Now I'm going to do this over here with a reflection property. So again, you got this 5 miles to point H, 6 miles, 6 miles to point farm from the river, and here to here is 3 miles. If you were to reflect either the farm or the house across. I'll just do the farm here. So again, nice perpendicular. All right, do a reflection of that. And then you were to draw a line straight to that reflected point, right? A nice straight line. That'll minimize your distance. So, this minimal distance, gonna just make a little right triangle here. So this would be 5 then, this distance here. And this is 3. So we have this right triangle in this picture, where it's 3 here, across from the house to the farm, horizontal distance parallel to the river. And then from this point here to that reflected point is 11 miles. And then our minimal distance is, the square root of 121 plus 9, right, using the Pythagorean theorem. 121 plus 9. So the square root of 130 miles will be the minimal. It's almost like, remember, the shortest distance between 2 points is a straight line. It's kind of like that concept. So I'm going to end up with the square root of 130 when we're done with this. Now, that's without calculus. But this is, supposed to be a calculus class. So let's go through and do this. So I don't know how far this point P is that we want to figure out where does this point P need to be so that the sum of these two distances is smallest. So again, this unknown, I'll call this X miles. And then if that's X miles, this distance here to the other end would be 3 minus X, right? Because again, it's 3 miles across here from in line with the house to being in line with the farm. So then again, I'll call it capital D, and this will be D of X. So the distance from H to P is just the hypotenuse of this right triangle. So that'd be the square root of 25 plus x squared, right? 5 squared plus x squared, square root of that. Or 25 plus x squared, to the half power. And then this e to f, again, it's this right triangle. So I got another hypotenuse, so square root of 6 squared, 36, plus, 3 minus x squared. So there's a distance function, right, of just one variable. Now the restriction here, right, my domain for this problem is, I could have x be 0, the farmer could walk straight to the river, due north, and then to the farm. So x could be 0, or x could be 3, right, where the farmer walks straight to this point here and then due south to the farm. So the restriction on x here is from 0 to 3. Now at the ends, so again, now we're trying to find the minimal distance. So at the ends, this distance when x equals 0, that'd be 5. You walk the 5 miles there, right? Square root of 25 plus 0, plus, and then 36 plus 9, square root of 45. That'd be the distance from this point directly north of the house to the river to the farm. I just replace x with 0 here. This would be 3 squared, 9 plus 36, square root of 45. So that's how many miles it would take if we did that. We'll get a rounded version of this. And then d of 3, and replace x with 3. This would be 3 squared, which is 9. 9 plus 25. That'd be the square root of 34. So that'd be from the house to this point when x is 3. and then plus 6. All right, because again, when x is 3, this is 0. This becomes square root of 36 plus 6 miles. All right, and we'll punch those in later, see what those are, and if any of them is the minimum. Now, critical points. Critical points would be a little... Hmm, you could talk... you could simplify this a little bit by saying, hey, this is a non-negative quantity. This is a non-negative quantity. So instead of minimizing these, you could talk about minimizing the sum of their squares, and then be working with a polynomial instead of roots like this. But we can keep it this way. All right, so I'm going to try to find critical points, leaving it the way it is. So again, d prime. So remember, this would be half this to the negative half, then times the derivative of the thing inside. That'd be 2x in the numerator, but because I had the half earlier, that's making that x. Again, I'm kind of rushing this, I'm sorry, but this would be half of this to the negative half. So give me this square root of 25 plus x squared down here. And then this, pretty similar, where be half of this to the negative half, right? So puts this in the denominator with a 2. But then when I take the derivative of the thing inside, this be 3 minus x. Well, times negative 1, because, times the derivative of 3 minus x as well. So that would just be x minus 3. So there's the derivative of our distance function using the chain rule and whatnot. And then, this is never negative, so this is not undefined anywhere. Same thing here. This is sums of positive stuff. So you're not going to have anything that makes this undefined. Any value of x that's real. So where is this equal to 0? Well, this will be equal to 0 when x over the square root of 25 plus x squared is equal, again, we'll just add this to the other side, so that's why I left it with the minus here, is equal to 3 minus x over the square root of 36 plus, 3 minus x squared. Yeah, this is kind of daunting. I mean, if I do cross products here, right, we got a proportion. It's be very algebra heavy. So that equals, and then 3 minus x times the square root 25 plus x squared. Then to get rid of the square roots, I would square both sides. Turns this into x squared times this quantity here inside the radical. And then here we'd have 3 minus x squared times, and then 25 plus x squared. And then if I multiply this out, so this would be 36x squared. So bear with me here. And plus x squared times this 3 minus x squared. And over here, I'd have positive 25 of that. There'd be 25 of this 3 minus x squared. And then, I'm just putting this into this. So 25 of this 3 minus x squared. and plus x squared of this 3 minus x squared. So you see this x squared times 3 minus x squared on both sides. We can subtract that away. And now I have two squares that are the same. This is 6x squared equals 5 times 3 minus x squared. So this is going to happen in one of two ways. If 6x equals, negative 5x plus 15, or if negative 6x equals negative 5x plus 15, either these things being squared are the same or they're opposites. Plus 15. So from here I'm getting x equals, 15 elevenths. I'm going to add 5x divide by 11 would be miles. And then here, getting x equals negative 15, which can't happen. Remember, x has to be between 0 and 3. X is a positive quantity. So that's not happening. So the only value x could be that will minimize the distance is this 15 elevenths. And then I would plug it in. All right, so I'm going to go to the function now and we'll plug this in. And we're going to end up seeing, you'll see. All right, so I go to the function. I'm very algebra heavy that if you're doing it that way. So this was capital D of x, equals, and then I had, square root 25, plus x squared. That was the distance from the house to the river, the point P on the river, plus, and then the square root of 36 plus quantity 3 minus x squared, right? That was the from the point on the river to the farm, and we're restricting this from 0 to 3. There, that's it. This little piece of graph here. So remember I said on the left end, all right, when x is 0, you got 11 points. Now that was that 5 plus the square root of 45 I had earlier, right? 5 plus the square root of 45 is what happens when you get 0. And then at the other end, see I got 3 with 11.83 miles for the distance if I walked to that one point, directly north of the farm. And that was that square root of 34, plus 6 that we had earlier, right? The 11.83. So see how this points out a minimum. The minimal distance here is 11.40, and I said that that would be the value of this d function at 15 elevenths. See, it's minimal distance is this 11.401. But remember, I said earlier with that non-calculus method with the reflection property that that's just I could have plugged it in. I just didn't feel like it for now. So that's the square root of 130. All right, if you reflected one of those points across the river and then just drew a straight line, that's your minimal distance. So I found it in a very roundabout way and got the same thing. So because I didn't punch it in, I'll put in 11.40 because it did say I could round to 2 decimal places nearest hundredth. So the minimal distance the farmer could travel, this person could travel to the farm, to the river, and to the farm is 11.40 miles, square root of 130. Right, so they do all that same stuff. Yeah, so they kept it with the roots and all that. And yuck. All right. So 15 elevenths. Yeah. All right. All right. So this is another one with a diagram drawn for us. So Beth is staying in a cottage along a beautiful and straight shoreline. So there's this cottage over here, shoreline that's 4 kilometers long, or at least 4 kilometers. A point Q on the shoreline is located 4 kilometers east of the cottage, and an island is located 2 kilometers north of Q. All right, so there's this point Q, 4 kilometers east of the cottage. This island that's 2 kilometers north. All right, so Beth plans to travel from the cottage to the island by some combination of walking and swimming. So she can start to swim at any point P between the cottage and point Q. If she walks at a rate of 7 kilometers per hour and swims at a rate of 3 kilometers per hour, what is the minimum possible time it will take Beth to reach the island? All right, so again, this is not minimal distance. They said you're minimizing the time. Because if you wanted to minimize the distance she travels, you would just go straight from the cottage to the island, right? The shortest distance between 2 points is a straight line. They're not asking for shortest distance. They're asking for the shortest amount of time. Where would I have to walk down the shoreline and then start swimming to minimize time? All right, so here's that diagram again. I'll put C for cottage, Q for, this point Q they mentioned. This is 4 kilometers, this distance from C to Q. And then there was this, perpendicular to this, due north, this island. I'll just put point I for island. And they said this was 2 kilometers due north. All right. So again, this is shoreline, and then this is, water out here beyond the shore. So what they're describing is person walks, so this is walking until some point P, and then from that point, swim to the island. Now let's assume there's not a crazy current and you can just go straight there. And what we're asked to do is, now the other info they gave us too was that this person walks, the walking speed is 7 kilometers per hour. And then their swimming speed was only 3 kilometers per hour, I believe. Yeah. So we're asked to minimize, get there in the shortest amount of time. Again, not the shortest distance, but the shortest amount of time. So I'm going to call this capital T. Now, you have to remember something here, that if you want time, you need to remember distance is rate times time, so you need to take distance divided by speed, distance divided by rate to calculate time traveled for. So you gotta remember that. All right, so just like in the picture with the last picture, this distance that we have traveled here, that this distance she walks along the shore, I'm gonna call that x kilometers, right? I don't know how long that is. And then this distance that's left over would be 4 minus x kilometers. Right? Because the whole thing from C to Q is 4. So that's x, that's 4 minus x. So then this length here, all right, so the distance she walked was x kilometers, so the swim distance would be the hypotenuse of a right triangle. So that swimming distance would be the square root of 4 plus, 4 minus x squared. And if you want to multiply that, you can. I'm going to leave it that way, though. All right, so this will be time in terms of x, t of x. So remember so you got your walking time plus your swim time. And again, time is calculated as, the distance you travel divided by your average speed, your speed. So the time it takes to walk from C to P, that'd be x kilometers divided by the walking speed, which is, 7 kilometers per hour. So 1/7 x, or x divided by 7. Simple. All right, this one doesn't look as simple. The swim time is the distance swam, which is the square root thing here, the hypotenuse of that right triangle. So the square root of 4 plus, this 4 minus x squared. Again, I'll leave it that way. You can multiply it out if you want. Divided by the speed. And the speed is, 3 kilometers per hour. So here's my time function. Now the domain of this, the domain of this got to be 0 to 4. Remember what x represents? The distance walking between C and Q here. So x could be 0, meaning I don't walk at all and just swim to the island. Or x could be 4, where I walk all the way to point Q and then swim. So then we check the ends. Now the time it would take when x is 0, so that would just be the time it would take to swim all the way across. So that's going to be 0 divided by 7, so no walking time. And then the swim time, you have 4 squared, 16 plus 4 is 20, square root of 20 divided by 3, and this will be they said kilometers per hour for the speed, so this will be hours. So that's how long it would take, whatever this is, to just swim there. And then if I walked all the way to point Q, that'd be the other end, right? Plug in 4. This would be, 4/7, 4 miles divided by 7, so 4 kilometers divided by 7 kilometers per hour. That's how long it would take to walk. Plus, and then 2/3. Again, 2 kilometers just to go swim, 2 kilometers over the 3 kilometers per hour. And if you want to put these together, this would be 12 plus 14, that's 26 21sts, hours. So that would actually be a shorter amount of time. Because, square root of 20, that's between 4 and 5. So this is between, 1 and 1/3, 1 and 2/3 hours, between an hour and 20 and an hour and 40 minutes. This is 1 and 5/21sts, and 5/21sts would be smaller than a quarter, so this would be less than 1 hour 15 minutes. So this is a shorter time at the moment, and hopefully that makes sense because she walks faster than she swims, so if she walks most of the way there, and swims, it should be a shorter time than if she just swam the whole time. Now these are fine, right? So far this is the winner, the smallest time, but there's got to be some point P in here where I can walk to it and then swim and get an even faster time. Right, so that's where the critical numbers are coming in, right? You got to find where is the derivative 0 in between here and here. So again, now I'm finding the derivative. So first term here is just 1/7, right? That's a linear x over 7, so it's 1/7. And then this, like the square roots before. Now if I take the derivative of this, again, it's going to be half, so I make this 1/6 times this to the negative half, which will put the root in the denominator. So this root of 4 plus 4 minus x squared in the denominator, and times 6, but then times the derivative of the thing inside, which will be 2 times 4 minus x to the first times -1. So you got a minus, and then 2 goes into the 6 down here 3 times, and you'd have this 4 minus x here. All right, so again, that's the derivative of these terms. And because this is a positive thing, you're never going to be divided by 0. It's not undefined anywhere. So I'm going to worry about where is this equal to 0. Now this will be equal to 0 if again, if I just add this fraction here, that's when 1/7 is equal to 4 minus x over 3 times the square root of 4 plus, 4 minus x squared. So again, I do cross products. square both sides. So 3 times the square root of 4 plus, 4 minus x squared must be equal to 7 times, 4 minus x. Square both sides to get rid of that square root. That'll give me 9 times this 4 plus 4 minus x squared quantity equals, and then here 49 times, 4 minus x quantity squared. And I distribute this 9, and so I'd have 36 plus 9 of this. Then I would take that away to get 40 of this quantity 4 minus x squared, and then divide by 40. That'll be 9 tenths. All right, 4 times 9, so 9 tenths, 0.9 equals 4 minus x squared when you isolate the square. Square root of both sides, so 4 minus x is going to be positive or negative square root of 9 tenths, which I'll leave that way. And then I subtract this. So x is going to be equal to 4 plus or minus the square root of 9 tenths. But the only one that makes any sense is the one with the minus. Because 4 plus the square root of 9 tenths would be too big. Remember, x can't be bigger than 4. I can't walk more than 4 miles here beyond point Q. So the only one that makes any sense is when x equals 4 minus the square root of 9 tenths. I think that's what they want, right? They want to say, says she can swim in 8 point blah, blah. Okay, so what is the time? What is the minimum possible time? So now I plug this in. So what is the time at 4 minus the square root of 9 tenths, and see if it's smaller than those values at the ends with the square root of 20 over 3 and the 26/21. So I'm just going to go to Desmos here, punch this in. So again, here was our function. So again, I called it capital T, right? We have T of x equals, and we had, the walking time, x divided by 7, plus, and then the swimming time was this square root of 4 plus, 4 minus x squared in parentheses, all inside the square root there, divided by 3. And we restricted x to being between 0 and 4. Okay, and so that's all we're looking at. So look, the ends are not the lowest, right? The left end is at that 1.49. That's the square root of 20 divided by 3. If I took the square root of 20, divided by 3, that was the value at the left end, 1.49071. See, the value at the right end is this 1.2381. That was the 26/21. 20. Yeah, 1.238. They rounded to 4 decimal places, 1.2381. So that was the 26/21 hour. So you see there is a lower one. And you see that's at this 3.05 value. And it would take, 1.17 hours when you round to 2 decimal places. So if she walks 3.05 miles down the shore and then swims, it'll cut her time to the smallest possible. Now look, this 3.05132, right? I said that would be 4 minus the square root of 9 tenths, which is just 0.9. See, 3.05131. See, 3.0513. Well, they rounded 132. So again, I'm gonna put the one rounded here, 1.17 miles or hours. Sorry, it would take her 1.17 hours to get to the island if she walked, 3.05 miles or so down the shore. So the number of hours, 1.17, rounded to 2 decimal places. They said 2 decimal places. Yeah, nearest hundredth of an hour. Cool. All the same stuff. All right, so here's another diagram. This time you got, looks like a rectangle with a semicircle on top of it. So we're doing the optimizing area or volume again here. So a Norman window, constructed by adjoining or attaching a semicircle to the top of a rectangular window, as shown in the image below. What is the maximum possible area in square meters of a Norman window with a perimeter of 76 meters? And then again, enter an exact answer round to the nearest tenth this time, so just one decimal place. This time they want the area, not just the dimensions, right? What is the maximum possible area? All right, so I'll draw the diagram they got here where you got, these lengths on the side of the rectangular X and the other lengths are Y. And you got this, again, semicircle on top, half circle. So you got this rectangular window here, and then, semicircle on top. They call this Y, this X, and this Y. So remember the radius would be half Y then, right? The radius of this semicircle would be half this Y length. And so when we're talking perimeter, right, they told us the perimeter of this window, the distance around it, must be 76, I think it was 76, yeah, 76 meters. So an expression involving perimeter here, well, if I walk around this, you got X and Y and X. So that's 2X plus Y. And then you got this half circle. So again, this is half the circumference of a circle. So that would just be pi times the radius. Remember the circle, the whole circumference is 2 pi r. So half of it would just be pi r, and r is half y here. So plus another half y, or half pi y. All right, again, pi r, pi times half y. And this needs to be equal to, 76. Now, if you want to put the y stuff together, you could, right? This is 2x plus, and then this would be, 1 plus pi over 2 times y, if you pull the y out of both of these. Must be equal to, 76. All right. So now we're asked to maximize the area. So find the largest, given this condition that the perimeter has to be 76 meters around here, find the maximum area. All right, so I'm going to call that capital A. So got the area of the rectangle. All right, so the space inside the rectangle would just be x times y, square meters, plus, and then this half circle. So remember that'd be half pi r squared, right? Half area of a circle. So that's going to be plus half of pi times, and then again, r is half y. So half y, squared. All right, so we simplify this a little bit. This is x times y for the area of the rectangle, plus, and then half squared. That'd be a half times a quarter. Be 1/8 pi y squared. Okay. So now we have our little area formula, but it's in terms of x and y. It's in terms of x and y. What I would like for it to be, just in terms of one variable. So I'm going to take my condition here, solve for one of the variables. Now I think the easier one to solve for would be x this time. So you see x would be, I'd subtract, right? You'd subtract this thing and then multiply everything by a half. So half of 76 is 38, and then minus, and then when I do half of this, you'd have a half plus pi over 4, distributing the half in there. times y. All right, so then this expression is going to go in for x. All right, so now it's going to turn this into a function of y only. So I got the area in terms of y is this, 38 minus half plus pi over 4 times y, then times, y again. Again, this was all replacing x. Then plus, pi over 8. I'll just put pi over 8 instead of 1/8 pi. Pi over 8 times y squared. And what I have here is a quadratic. Now the value of y, and there's definitely a limit to it. But this will be, I'm gonna just enter this. It's a quadratic, a parabola, and we're gonna look at where the maximum is. Again, I would multiply this out. Maybe I should just do it. Again, if I multiply this out, you got 38y, then minus this, half plus pi over 4 times y squared, but then plus another pi over 8 y squared. And this is really, this is minus half pi squared, y squared minus pi over 4, which would be minus 2 pi over 8. But then plus pi over 8 would be minus, so this would turn this into plus pi over 8. You got 38y. Again, the minus half y squared minus pi over 4y squared, then plus the pi over 8 would make that minus pi over 8y squared. So then I've got, minus a half plus pi over 8 y squared. Again, this will be some quadratic parabola thing opening down, right? The coefficient on y squared is negative. So it's going to have a maximum. And if I were to do the derivative and see where the derivative is 0, that's where the maximum will be, and then we can plug it into this. But again, I'm going to go to Desmos and enter this, and I'll use x instead of y. But just remember, maybe I could plug in y. But a prime, that would be 38, and then power rule here. So minus, and then when I double this, it would just be 1 plus pi over 4. Double each of those times y. And when is this equal to 0? This is equal to 0 when y equals 38, divided by this 1 plus pi over 4 value. So you're going to see this is the input for the vertex of this parabola. But let's go into it. And then I would plug this in, and I'm going to round to the nearest tenth. All right, so here is our area function. All right, so the area, maybe I could do a of y equals, and we had, well, again, I'll just put out the multiplied version, 38y. Yeah, so we're good with y here as the input. Oh, no, we're not. No, we're not, because that didn't look good. All right, I'm going to do x. All right, I'm going to use x instead of y. 38, yeah, because it should be when x is 1. When the input 1, the output 38. Maybe even use a different letter just so you don't confuse it with x. Maybe t, 38, t. Right, still, when the input's 1, the output. When I used y there, it gave me like the inverse or something. Right, that's not good. So I'm using t instead of y. All right, t instead of y. So I have 38t minus, and then this 1/2 the quantity 1/2 plus pi over 8 times t, and again t instead of y, t squared. And if you look for the top of the hill on this thing, all right, it's way up here. I'll change the color up too. There it is. So the largest area you could possibly get here is 404.4, right? If you round to the nearest tenth, 404.4 square meters for the largest possible area of this, Norman window with a perimeter of 76. Now look at the input here, 21.28377. Remember what we got after taking the derivative and setting it equal to 0 is 38 divided by this 1 plus pi over 4 value to the 28.28377, right? See, 21.28377 rounded to 5 decimal places. So I found that value, but then needed to plug it into the function and get this 404.4. Round to the nearest tenth. So in the largest area, I'm going to put the 1 rounded to the nearest tenth here. The maximum area possible, 404.4. Let me just double check that, make that right. Yeah, 404.4 square meters. Cool. All right, so another area volume thing. Okay, so this one's asking for maximum volume. All right, so I did a problem like this earlier where, it was a piece of plastic, you're cutting squares from each corner. I think that was a 12 by 36 inch piece or a 12 by 30. So this is 12 by 42, open top box. What's the maximum possible volume? I'm just going to go into the volume. So like, remember the volume in terms of x there, if you cut out squares of corner size x by x and then fold it up, the height will be x. And then, one of those sides on the base will be 12 minus 2x. The other side will be 24 minus 2x, right? The base was 12 by 42 minus 2x. And that would be the volume of any box I made. And of course, it would have to be restricted from 0 to 6 because one of the sides is only 12 units long. And let's find our maximum here, right? Let's go to the top of this hill here. Pretty high. There it is, right? So the maximum volume possible is when I cut squares of this size, 2.755 by 2.755 inches out of the corners. And our maximum volume would be, 652.44 if I round to the nearest hundredth. So maximum value 652.44 cubic inches. Just double check that. Yeah, that's the top of that hill. Great. So again, very similar to a problem I did earlier. I just didn't feel like going through it again. All right, so this time surface area. So another one with a square base and an open top for a box, but this time it's about how much, the material costs, right? You're trying to minimize cost. So what is the minimum cost of, putting this box together? So you've been asked to design a rectangular box with a square base and an open top. The volume of the box must be 210 cubic centimeters. The cost of the material for the base is 70 cents per square centimeter. And the cost of the material for the sides is 60 cents, $0.6 per square centimeter. All right, so we're asked to determine that, basically find what's the smallest cost possible and give your answer in dollars, round it to the nearest cent, which would be the nearest hundredth. So again, very similar picture to one we saw before, right? I got this open top box with a square base that I'm putting together. Again, this is open, so nothing on top. And I'll call this X by X because it's got a square base by Y, and these were in centimeters. Because they gave me that. And the volume of this, which is X squared times Y, had to be 210, square centimeters. Or sorry, cubic centimeters is the volume, cubic. So that's all the information given. Besides the cost too. Now the bottom, right, the base. So the base costs, $0.7, right? 70 cents per square centimeter. And then the sides, the material on the sides costs 0.6 or 60 cents per square centimeter. And we're trying to minimize cost. So here's my cost function. I'll put C for cost. Now C, I take the area of the base, which would be x squared. So that's how many square centimeters make up the base, and then multiply that by 0.7, right? So this is how many dollars it's going to cost to make the base. And then add to that, there are the four sides around, which each have an area of x times y. But then so that's how many square centimeters there are around the four sides of the box. Again, the top is open, don't worry about that. And then each of those sides costs, $0.6 per square centimeter. So I multiply that by 0.6, and this will give me my cost. Now, y should be 210 divided by x squared, right, from the volume information. And I'm going to put that here. So our cost in terms of x is 0.7 times x squared plus, and then 4 times 0.6 be so this would be 2.4, but then times 210. So 2 times 210 is 420. 4 times 210 is 840, but it's a tenth of that, so plus 84. So that'd be 504. So this would be plus 504 over x, right? Because again, we have x over x squared. So here's our cost function. And again, value of x has to be positive, and we're trying to, it's just got to be positive, right? And we're trying to minimize the cost. So again, you could take the derivative, or I did a problem like this before. Take the derivative, find the critical point. And we're asked to round to the nearest cent. So I'm just gonna go and punch this in, look at it for positive values of x, and determine the lowest cost needed possible. So again, I would call this C of x equals, our cost function 0.7 x squared plus 504. Just so just so I don't make a mistake with the, I might have made an arithmetic error. We'll see. I had 0.06, times 4 times 4x, and then times 210 over x squared. So that was all over x like that. Okay. Now if I restrict this to just positive values, just look to the right side of the axis here. There, this is the part of the graph we'd be on, right here. And there's definitely a lowest cost, and that'd be $106.27 if I round to the nearest cent. And that'll happen when I, make the base a 7.11 by 7.11 centimeter base. But they're asking for the lowest cost, right? This was the cost function. So the lowest cost, given these restrictions, $106.27 rounded to the nearest cent. And you would normally do calculus. I've done a bunch of problems like this already. Just trying to save a little time here at the end. Okay, great. All right, so another one all right, so this is very similar. Box, square base, open top. Volume must be 540. And these are the costs. So all that would change to give me the smallest cost. Right, remember this had 70 cents for the bottom, 60 cents for the sides. This is 90 cents for the bottom and 10 cents for the sides. So I would change that to, so instead of 0.7x squared, 0.9x squared. And then instead of 0.6 here, 60 cents for the sides, it's only 10 cents for the sides. And then the volume was supposed to be 210 in the last problem. Here, the volume of the box is supposed to be 540, so I'm kind of glad I wrote it this way. So now I just replace that 210 with 540, and here we go. Again, to the right side, only for positive values of x. The lowest cost open top box I could make would cost me $65 and about 69 cents if I round out to the nearest cent. So $65, 69 cents. Again, you would set that up, take the derivative, find critical points and all that. But I've already done enough of this. All right, so 65, 69 would be the lowest cost rounded to the nearest cent. Right. All right, so the distance or travel time. Okay, so here, two poles are connected by a wire that is also connected to the ground between the poles. The first pole is 4 feet tall, second pole is 5 feet tall. There is a distance of 7 feet between the two poles. How far from the first pole should the wire be anchored to the ground to minimize the amount of the wire needed? So this is that one where I could use the reflection property, which I will do here. Just go back and look at that first problem on the minimizing distance. So here's what's going on. You got the ground. You got one pole that's 4 feet tall. And then you got another pole that's 7 feet away. Right, so there's 7 feet between the poles. So from here to here is 7 feet. And then another pole that is, 5 feet tall. So a little taller than the other one, says 5 feet. And then it says there is a wire connected to the ground between the poles. So wire to the pole, wire to the ground, anchoring that pole, and then also, anchoring this pole. So what's the shortest wire needed? They're saying minimize the distance, minimize the amount of wire. All right, so there's this wire, minimize wire. So again, I could do this thing where we reflect. We're talking about minimizing distances. You could use a reflection property, reflect this 5-foot pole into the ground here, and then just draw a straight line distance from the top of the 4-foot pole straight there. You create this little right triangle where again this is 5 feet, 4 feet, this is 7 feet. So you got a right triangle here with 9 feet on one side, 7 feet on the other. So the minimal distance, the minimal length of wire from here to here to here, 81 and 49, 130, right? Square root of 130, which again, not always square root of 130. It just happened to be the square root of 130 for both of these. Right? So the minimal distance is the square root of 130 feet. Again, 81 plus 49, 120 and 10. Right? So let's enter an exact answer or round to the nearest foot. So I'll just put the square root of 130. Oops. Okay, maybe I rushed that. Two poles are connected by a wire that is also connected to the ground between the poles. How far from the first pole? Okay, my apologies. They didn't ask for the minimal distance. They didn't ask for the minimal distance. They want to know how far from that first pole, should it be so that you get the minimal distance. So my bad. And so we may have to. Oh, I can just set up a little proportion here, right? I'm gonna take this right triangle. And now we know this minimal distance here, square root of 130, and the big length over here is 9, right? 4 and 5. This bottom length is 7. So what's this? Now these are similar triangles, and we know that this is a 4 to x. All right, 4 to x. So 4 to x should be the same as 9 to 7. Don't even really need the square root of 130 there. So 9x is 28. X needs to be 28 ninths. So this needs to be 28 ninths feet, a little bit more than 3 feet away from the first pole. get that maximal distance. So again, sorry I didn't read it carefully. I'm just it's been almost two hours 20 minutes here. Sorry about that. Just kind of trying to rush through. So I should have read the thing right. Feet from the first pole. That's 28/9, and the first pole was the 4-foot one, right? Yeah. So 28/9 feet. Yeah, that's better. But that minimal distance, right? The minimal length would be the square root of 130, which they might discuss here. They don't. All right. Okay. All right. So this is very much like the problem from earlier. Where again, I'm going from a cottage to some point on the shore here and then swimming to this island. And it's still 4 kilometers, 2 kilometers, so not a heck of a lot would change from this picture here. Let me pull that up. I got my paper for that problem from earlier with the shoreline and the island. So that was this here. It's the same picture. Still 4 kilometers here, 2 kilometers there. The only thing that would change are the speeds. So instead of 7 kilometers per hour walking, well, it's still 7, but the swim speed is now 6. So now this changes to 6 in my time function. So all the stuff I set up for this problem earlier, it's the same time function. Now that of course would change things down here and where the critical point is and all that, but I'm just going to enter this function in Desmos and we'll find our minimal time. And I think that's all it wants. It says what is the minimal possible time, right? What is the minimal possible time it will take Alex to reach the island? Again, walk down the shore, swim for a little bit. All right, so back in Desmos, I will enter a very similar function to that one from earlier. So time in terms of x here, again, x, that was the walk distance divided by the walk speed for the walk time, x divided by 7, plus, and then you got square root of 4 plus this 4 minus x squared quantity. That was the swim distance divided by the swim speed, which is now 6 kilometers per hour for the swim time. And restricting this to just 0 to 4 again, you could only walk up to 4 miles down the shore, and that's what x represented. So 0 less than or equal to x less than or equal to 4. All right, and there's that piece there. So there's clearly a smallest point, right? Not much smaller, but you see how if I just swam, would take 0.74, 0.75 hours, whereas if I walk a little over 2/3 of a mile down the shore, 0.67 miles, and then swim, it'll take 0.74 hours. So a little quicker. And then of course it takes longer to go all the way down the shore and then swim across. So the minimal time here in hours would be 0.74 when rounded to the nearest hundredth. So 0.74. Great. All right, then the last objective is in that abstract scenario. All right, so that's the other. So those were all with geometry involved, triangles, semicircles, rectangles, right? So now we got this, in the abstract, solve optimization problems with no real geometric setting. So they're just giving us a, some random scenario, and we got to minimize or maximize something. So here a rectangle is inscribed with its base on the x-axis and its upper corners on the parabola y equals 49 minus x squared. What are the dimensions of the rectangle, the greatest area? And give the length of the rectangle as the dimensional on the x-axis and the width as the vertical height of the rectangle. And this is enter an exact answer. So here's what's being described here. Again, you gotta put, so they got this graph. And they said you're on the, here's the XY plane. And look at the graph of y equals, 49 minus x squared. So I would have a vertex at 0, 49, x-intercepts at 7, 0 and negative 7, 0, and be some parabola, opening down. Something like that. Now we're only going to look at the top part because what they describe to us says a rectangle is inscribed with its base on the x-axis and its upper corners on this parabola. So base on the x-axis. Again, let's call this let's call this the length. And its, upper corners on this graph. Now, because of the symmetry, sorry, that should be on the graph. I want to make this taller. There's the width, right? The height. Now, because of the symmetry, I've got to make 0 in the middle. Because if I had this shifted over here, right, the one height would be totally different than the other. You wouldn't have a rectangle, right? And they mentioned it had to be a rectangle, right? So this has to be the same as this. So due to symmetry, 0's got to be in the middle. So let's say this distance over here. So again, if I'm calling the length down here L, this would be L over 2. Now you could also just call it X, but this would be L over 2, this would be L over 2. And, when X equals L over 2, remember the height is just the Y coordinate here. So 49, the height would be, this width would be 49 minus, and then L over 2 squared, right? I would plug in, the X value here would be whatever half of L is. Plug that in for X. That'll give me the Y value, the height of it. So then the area of this rectangle that I would produce, and I'll call it A of X, or no, A of L, because I'm using L here, gonna be the length, so L, times, and then the height, the width, which is this 49 minus, L over 2 squared, and then we'll find the value of L that makes this, says, give us the one with the greatest area. Right, the one with the greatest area. Now, of course, L can't be bigger than 14. Right, L has to be ranging from 0 to 14 because again, the 2 points on the intercepts here on the ends are 7 and negative 7. That's a 4. So if I made it 14, there'd be no rectangle. So the highest it can be is 14. And I guess I could make it 0 and, that would still be no rectangle. Yeah, so then I'll multiply this out. This would be L. This would be 49 minus, 1/4 L squared. And if I distribute the L, that'd be negative 1/4 L cubed plus 49L. So I get this cubic polynomial here. So again, at the ends, the area equals 0, right? At the ends, there is no rectangle to speak of. So we got to find the critical point, right? So again, A prime, polynomial here would be negative 3/4 L squared plus 49. And so this is going to be equal to 0 at L equals positive or negative. It's got to be the positive one, right? Because that's what L represents, the length. I would subtract 49, multiply by, so L squared would have to be 49 times 4/3. But 3 goes into 49. Well, it doesn't go into 49 evenly, so that'd be a 160 plus 36, 196 thirds, and then the square root of that, which you could write that as like square root of 14 over root 3. But we got to use the positive one, right? So that's got to be L. And then the width, again, it's got to be half of this squared taken away from 49, right? That's what the width was. So I'm just going to enter those as is. Those will give me my largest area. So again, the length that would give me the largest would be 196 divided by 3, and then the square root of that, right? So raised to the half power. And then the width had to be 49 minus, half this length squared. So, 0.5, well, 0.25 is when I square a half, it'll be a quarter. And then this length squared, it'll just be 196 over 3, right? Because I'll get rid of the square root. And this should be good. I mean, I know it's not perfect, but it's equivalent to whatever they're going to have. Right. So yeah, they actually simplified it and stuff, but yeah. So another one. So here, at what point is the function, so some linear function closest to the origin? Enter an exact answer. All right, so we're going to closest means smallest distance, right? If you're closest to something. So we got f of x equals, negative 8x minus 8. That looks like this. It's a line with a slope of negative 8 going through the negative 8 here. So it's looking like this. You have 0, negative 8. You'd have negative 1, 0. Right? This is a rise, negative 8, run 1. So this line here. And then here's the origin. All right, they said which one of these points, so which point on this line, so take any point on this. So here's x and then negative 8x minus 8, right? That would be the y coordinate. We're going to minimize this distance. We'll call it d for distance, right? So when is d smallest? So when is d smallest? So again, the distance here, remember the distance between 2 points would be the square root of x minus 0, the change in x squared, so just x squared, plus, and then the change in y squared, which would be this negative 8x minus 8, squared. And then I could multiply this out, and again, I'm just gonna, it does say enter an exact answer. All right, so we gotta actually find this. Now, I think I mentioned this before. If you want to minimize, this is just a big square root here. This will never be negative, so it's a non-negative quantity all the time. We can minimize the distance squared then, if you wanted, d squared, and it'll be minimized at the same value. So if I get rid of this square root, we can just look at this function. D squared is x squared plus, then I'll multiply this out. And this would be 64x squared and plus 128x, and then plus 64. If I squared that. So we got 65x squared when you put things together, plus 128x plus 64. And then we take, so I'm going to call this, we're trying to maximize, let's call it y or something. So y prime, the derivative of this, would be 130 x plus 128, and this derivative is 0 at x equals, negative 128 over 130, so negative 64 65ths. So that's the x coordinate. So that'll be something a little bit to the left of negative 1 here, negative 64 65ths. So there, at some point around here, it should be perpendicular. When you draw the segment to 0, 0, that's how you determine what you're closest, when you're closest. And then y, and if I'm on this line, would be, negative 8 times negative 64 65ths, minus 8. And again, I'll just enter that for the y coordinate. But those are the x and y coordinate of the point on this thing that would be closest to the origin. So negative 64/65ths. And then, negative 8 times negative 64/65ths minus 8, right, for the y coordinate. And that should be good as the exact value, right? So that was negative 8/65ths. And they go through all that here. They kept the square root in it. But notice the numerator here is 130 when they do the derivative of the distance formula. Distance function, they got 130x plus 128. That was exactly the same as the derivative of our distance squared that I said earlier. So yeah, if you're trying to minimize a square root, you can minimize the square, and the minimal value will occur at the exact same input. All right, so here we're considering two non-negative numbers, so they're greater than or equal to 0, both of these, where x plus y is 11. What's the maximum value of 6x squared y? Enter an exact answer. So again, we got x plus y must be equal to 11. They said they're non-negative, right? And we're trying to maximize, I'll say f of xy here as a function of x and y equals 6x squared y. Or you can call this q for quantity, whatever. Maximize this quantity, this value. Now, this is a function of two variables. So I use my condition to make a substitution, right? You solve for y up here. Y would be 11 minus x. Put that in here. So now I have q of x, just a function of x, would be 6x squared times 11 minus x. And distribute, this would be negative 6x cubed plus 66x squared. And then I could take the derivative. Would be, negative 18x squared plus 132x. Both of these have x in common, as well as 2. Take out a negative 2x. Maybe times 9x minus 66. I could pull out a 3 even. So that'd be negative 6x times 3x minus 22. So this is equal to 0 at x equals 0 or x equals, 22/3. Now when x equals 0, this has a value of 0, this q thing. When x equals this is 22/3 is going to maximize this. Remember how because this is a cubic function that, would have an intercept at 0, an intercept at 11, and it's got a negatively coefficient, so it's got to be doing this, right? And it's going to touch here and bounce off because, got x squared as a factor multiplicity of 2, and then come up and then come back down, and do something like that. So there's got to be a maximum here at the 22/3. Got to be a highest value because, again, you can't go left of 0. Got to be non-negative values of x and y. So plug this in to our function, and I'm actually just going to do that. I'll plug it into this. So replace all the x's in here with 22/3, and that'll be our maximum value of this cube, this quantity they gave us. So 6 times, 22/3 squared, and then times after that 11 minus 22/3. Of course, they're going to simplify it, but as long as you enter something that's equivalent to what they have, it should be good. Great. Now the 10,648 divided by 9 would be that value. Okay. And then this is a little different. It's very similar, though, to the problem with, what point is closest to the origin, but it's closest to the point 1, negative 6. And again, we're asked to enter an exact answer. All right. All right, so hopefully this is the last one. Sorry, it's been 2.5 hours. Sorry about the rushing this, but all these are similar setup, where you're trying to, again, set up an equation for something you're trying to optimize, get it to be a function of one variable, and then, you're doing calculus, you're finding absolute extrema over some domain. So once again, this negative y equals negative 8x minus 8 line. So again, negative 8, 0, negative 8, negative 1, 0, right? This is the line in question. There's the graph of f. And they're asking us, what point is closest to 1, negative 6? Now, this would have 1, negative 16, so 1, negative 6 would be above the line, right? So there's 1, negative 6. And we're saying take any point on this curve which has an x-coordinate of x and a y-coordinate of negative 8x minus 8. Do the distance to this point here, and what's the closest? Now the closest should be perpendicular, right? If I draw the segment, it looks like 0, negative 8, but it might not be. All right, we'll see. So again, the distance, and this distance here, and the distance will be, here's the distance formula, square root of, x minus 1 squared, the change in x squared, plus, and then the change in y squared, negative 8x minus 8 minus negative 6 would be negative 8x minus 8 plus 6. So that'd be negative 8x, minus 2 squared. And again, we can, when we're minimizing a square root, you can minimize the square as well and get the same location and get the same input that'll minimize it. So just look at this as a square, x minus 1 squared, plus this, negative 8x minus 2 squared. And honestly, it's going to be at the critical point, what's going to minimize this here. So I take the derivative, and that's, 2 times x minus 1 to the first, plus 2 times negative 8x minus 2, but then times negative 8 again with the chain rule. This is 2x minus 2, and this is distribute negative 16 here. Negative 16 times negative 8. 108, right? 16 times 8, 80 and 48. 128, 128, 128. So plus 128x. And then negative 16 times negative 2, positive 32. So I got 130x plus 30. And this is going to be equal to 0 at x equals, negative 3/13. So when x is negative 3/13, you'll be at the point that's closest, perpendicular if you draw the segment to the point 1, negative 6. So I'm plugging this in, and then again, just plugging in y would be equal to negative 8 times negative 3/13 minus 8, and I'll just enter that. So x coordinate of the closest point, negative 3/13, y coordinate, negative 8 times negative 3/13 minus 8. Should be good. Wonderful. All right, so that's it for this preview. So again, sorry I rushed that last part, but pretty long video. Hopefully watching me go through a lot of the first ones, right, where I actually do the proper setups, more slowly, will help you out when you're working on these assignments for maximizing or minimizing some quantity on your own. And thank you very much for watching.